Okay, so in this next video we're going to see why this value that we've constructed, why this Pearson's product moment correlation coefficient, which we've denoted the correlation of the two random variables h and m, why that can only take values between 1 and -1, basically. That's what this video is all about. Okay, so firstly, let's just have a reminder. We have our abstract probability space here, which we are thinking of in terms of the population, the human population. And we're thinking about, we've got these two random variables, h and m, height, which describes the height of each person to each person. So every person has a height. This will ascribe a real number to every person. And mass, which is ascribing the mass, which is a positive real number. And it's going to ascribe that to every person in kilograms and in meters. Okay, so we've discussed how the correlation of h and m is best viewed as being equal to the covariance of the standardized random variable. So if you construct from this another random variable by taking the height of your person, subtracting the expected value of the height, and then dividing by the standard deviation of height, that produces a standardized random variable. Instead of ascribing to every single person their height, what it's going to ascribe to you is the number of standard deviations you are within the height, and it will ascribe you a positive value if you're above the average value, and it will ascribe you a negative value if you are below the average value. So it will tell you how many standard deviations you need to go either up or below the mean value of height to get to your value of height. And we're going to call that standardized variable h bar. And similarly, we can construct one for mass. We can take the mass, subtract off the expected value for your mass, the mean value, and then divide by the standard deviation of the mass, and that will tell you how many standard deviations you are within the average mass. And we'll call that random variable m bar. So we're taking the covariance of these two standardized random variables here. So we could write this as being equal to the covariance of the random variable h bar with m bar. And we want to see, why is this covariance of these two standardized random variables always going to be within -1 and 1, basically. Okay, so the way of seeing this is if we consider another random variable, which we can consider over here, which is h bar plus m bar. So that's a rather abstract, funny thing to consider. We're considering adding the number of standard deviations that you are away from the average height to the number of standard deviations you are away from the average mean. But nevertheless, it is something that you could construct, and you could ascribe every person on the planet a value of h bar plus m bar. Now, if we consider what the variance of this random variable h bar plus m bar is, that's going to be something quite interesting. Now, remember from the properties of covariance that this is equal to the covariance of h bar plus m bar with itself, i.e. h bar plus m bar. And if we expand this, then we can use the distributive properties. If you aren't familiar with this, see my videos on properties of the covariance. Then we can expand this as the covariance of h bar with h bar plus 2 times the covariance of h bar with m bar, because you'll get the covariance of m with h bar and the covariance of h with m, you'll get to the covariance of m bar with h bar and the covariance of h bar with m bar, but they're the same thing by the symmetry properties, and plus the covariance of m bar with m bar, basically. Now, these two terms are the variance terms. So this is the variance of h bar, this term here. Then we've got plus 2 times this covariance of h bar m bar, and then we've got plus the variance of m bar. But because m bar and h bar are standardized random variables, those variances are just equal to 1. So we get that this is equal to 2 plus 2 times the covariance of h bar m bar. Now, we don't know much about what the variance of h bar plus m bar is, but there is one thing we know, that variance is always greater than or equal to 0, because you are taking, remember, the expected value of a sum. So if you take the variance of x it is equal to the expected value of x minus the expected value of x. Sorry, what did I say? I think I said the expected value of sum. You're taking the expected value of a square, of a sum of squares, basically. So you're taking the expected value of a random variable, which is always non-negative. Therefore, the expected value, how can, for instance, if you take the height is a random variable which is always non-negative. If you take the expected value of a non-negative random variable, you would not expect to say that the mean value was -1, would you? Because this is always non-negative. Similarly, x minus the expected value of x squared is always going to be non-negative. So this expected value is always going to be non-negative as well. So this is always going to be greater than or equal to 0. So we can say that this is always going to be greater than or equal to 0. So that implies that 2 plus 2 times the covariance of h bar and m bar has to be greater than or equal to 0. So that implies that the covariance of h bar m bar, so if we move the -2 onto the other side, we get that 2 times the covariance of h bar m bar is greater than or equal to -2. Then we multiply both sides by half. You're allowed to do that within the axioms of an ordered field, and you get that the covariance of h bar and m bar is greater than or equal to -1. Okay, so that's how we can see that it's greater than or equal to -1. And the way that we can see that it's less than or equal to 1 is by considering another random variable. If we consider the random variable h bar minus m bar now, so that's another random variable. It's saying take the number of standard deviations you are within your height, and take away from that the number of standard deviations you are away from the average value of the mean. Okay, so if we take the variance of this new standard, of this new random variable, and again, these random variables are unimportant, but for the fact that they're going to help us prove something. So we're just proving inequalities here. This by the properties of covariance is just equal to the covariance of h bar minus m bar with h bar minus m bar. If you expand that, you get the covariance of h bar with h bar minus 2 lots of the covariance of h bar with m bar plus the covariance of m bar with itself. So again, we're just applying the distributive property and then using the negative signs because we can pull those out of the covariance, basically. So what, of course, you would get is the covariance of negative m bar with negative m bar. But again, we can pull both of those out by the first bilinearity property of covariance, and they'll obviously cancel to give you a plus. Here they won't, you'll get one of them, so you'll get the -2. Okay, so this is just the variance of h plus the variance of m, but those variances, because these are standardized random variables, these covariances are just going to be equal to 1 because they're equal to the variances. So this is going to be equal to 2 when we add them together, and we'll get 2 minus 2 times the covariance of h bar with m bar. Okay? Again, we don't know anything about this variance, but for the fact that it is greater than or equal to 0. So we know that this is greater than or equal to 0. So we set this side greater than or equal to 0. So 0 is greater than or equal to, 0 is less than or equal to 2 minus 2 times the covariance of h bar m bar. Now this time we take this thing to the other side, and we get 2 times the covariance of h bar m bar is less than or equal to 2, and then multiply through by half, and we get the covariance of h bar m bar has to be less than or equal to 1. So that is what we need. We have the two inequalities that we need. We have now got that that the covariance of h bar m bar, so we have that the covariance of this standard random variable h bar m bar is less than or equal to 1, and it's also greater than or equal to -1, and this is exactly equal to the correlation of h and m. So we have found, therefore, that the correlation, the Pearson product moment correlation coefficient for any two random variables h and m is within -1 and 1. So that is why we would say that it is a standardized version of covariance. It's going to give you a number which tells us about how correlated the two random variables are, and it's not just going to be some arbitrary real number. It's going to be a real number within the interval -1 to 1.